So for the final course project task is the task 6, and the second subtask is we have developed the program with for the adaptive white Gaussian noise channel simulation, and with our specific modulation type and the Codewords. We already simulated the without Hemi error correction code for the second and second subtask. We need to simulate the with the Hemi error correction code, and we already studied the 3 Hemi error correction code, which is we have group code, which contains the systematic group code or non-systematic code group code. We also have the cyclic group code, and so we have 3 different error correct code formats. And in my case, I will show all of them, how to add all of them, or for you, and you will just select your corresponding group code error correction code formats. That's enough. And let's come back to the first task. I would like to mention about so first task. We need to draw a diagram of the digital information transmission. So the idea is that we have some analogs. If we have some analog data, we will use the sampling theorem to convert the analog to digital data. Then we do some source coding, right? And after that, we do some channel coding. Then after channel coding, we will do some modulation, and we finish our transmitted data plot, and we send to the channel, and there during the channel transmission, there will lots of noise will add in our transmitted data. So for the received part, we will receive the modulated signal with lots of noise, and we will do some use some descriptor to detection, and we have to do the demodulation. After that, we use the channel decoding or source decoding. So that means our the Hemi error correct coding will base the before the modulation types. And for the octave, we have the first course project task 6, and it will give us 2 separate program, is the encoding function and the decoding function. And firstly, let's move to the task 6. And before we do some error correct coding, and we need some parameters. First, we need to know our control symbols, and so your code word, how many code word nets do we need to transmit, and which there are how many control symbols and how many data symbols were transmitted. So for the previous case, we have to know the code word names and the number of the checked symbols and the number of the data symbols. This is our prior knowledge we need to know, and we will add in here for so we can see here we will generate the yes, before the Here we will specify our error correct code. Coding parameters. We need to know our code word names, and in my case we use the 7, right? And please find your case in course project. How now is your code word names? Here your code word names, and in my case is the m equals 7. And we have to know the control symbol. We will use the function to find it, and we use a log2. And we know just the m+1, then we will get the control symbol. So after that, we will get the data symbol and use the code word names minus, then the control symbol. So, and after that, we will do some modification with the generated data, and I will move it. And we can generate the binary data randomly. However, we will limit by some code word names, which is the K. So for the K, sometimes it different. However, you will have the different K, which is so the total code word names is 31, and you minus your maximum code word names is 5, so it will your case 26. However, if we use the 1000 divided by the we transmit 1000 data divided by the 26, and you will see here it's not integer number, and we will do some uh, modification to make sure the k number should be the integer number. And yes, in my case, I use the 1,000 number, so transmit data. So for your case, it's better to use the 1 minute data. You just change the 5 to 6. It's okay. Here I only to hope to make sure that the program will run faster. And we have to generate data, and we will do some here. We will use some flow function. So n will be the flow is the divided by k, and multiplied with a k. So this step we update the number of the bits to be sent. Which is match information size. Information block size, and so we can do a test, which is the here we have you will see here, and in my case we use the float function. K is a 4. And you will see here after float, it's the same. However, if your K is the 6, no, 3, like we have the 26 or yes, if your K is the 26 and you will lose some transmitted data like 4 bits, you will lose this function. In order, we hope to get the integer number which matched our encoding regulations. So this is update the place here, and we have the modulation tab, and we do the modulation. So let's see what is the modulation, what do we need. So for the, if we want to do the modulation, we need to here this function told us we need to the binary data, which is the a matrix with the k rows. No, this is the k, which is the k columns and k columns, and each row represent a single data block to be coded. And we need to know the code word names and the information symbols per code word names. And we will do the here we will use the to do the matrix multiplication. And so here we need to specify our code word names. And so first we will talk about for the non-systematic code words. And in here we have already, this is second code, and we have to, we already know how to get our code word names. And we get the equation, encoding equation. After that, we reshift it. We get our yes here, and which we get the we reshaped it here like the E1, E2, and E3, E1, E2, E3. After that, for the data block, we automatically use the identity matrix for the dating. So this is my encoding matrix. And for your case, you will firstly you will find out your encoding matrix, and this is for the non-systematic group code. And I just type out them. So it will be the 11140. And for the 1001. Zero one zero one. And for the one. and now we can save it, and before the modulation we can do the such work with encoding. So we have to specify the uh, uh, for the encoding. We have to know the first parameter is the binary data, which is a matrix. So this will be the ham encoding. And for binary data, we use the reshape it. We reshape uh, the transmitted data here as B. Yes, we use it here. And this is a single row vector, right? We reshape it as some dimension. So for the row is the K, and the K is our uh, uh, K is our uh, data, and um, for the column we will use n divided by k, and after that we will do some reshape. I'll show you why we do need to do this. Uh, so this will be the map of the information blocks to be coded. And so suppose we transmit 10 data, which is 1 to 10, and no, we 14. So we can reshape it, and now we reshape here. The idea usually we will use that we just reshape it as the like we hope to get this one. So the first 7 bits will be our first row, and the last 7 bits will be the second row. And you will think about that our row we just need 2, and the column will be the 7. So however you will see this is not our desired result, and you can see here it changed from here 1, 2, 3, 4. It's not like the from the first 7 bits to the first column, first row, and the last 7 bits for the second row. So we have to do some uh, reshape here. Like firstly, we have to do use the we use the 4, and here we use the 4. After that, we use the 14. So we have 14 divided by 4. So in this case, 4 with here will be the yes here how to say okay is the 14 divided by to use some okay and so we just let's back to here, which is the k will be the 4 or 3. Cannot we convert that to the 4? Anyway, okay, so we can do it here, and after that we will come back to see and the encoding data. We will use the encoding function and here, and we just yeah, and use the m and k, which is after that we will see here okay, so flow. Okay, I just want to hear flow. We have it. So flow. 14 divided by the 4 and multiplied with the 4. Oh yes, here we use the 12 and we reshape it as the 12 and it's 12 divided by 4, this will be 3. So why it cannot 12 divided by, we use the flow and here is the so we reshape it as the access the that is 4 and for which okay, so it shows some okay, we just specific here, which is and after that we would here and you will see here like this, and it will follows by some order and we can do the thing we so previously our reshape will be the 1 2 3 4. After that we will do the 1 2 3 4 5, 6, 7, 8, and we can use some single with the convert them as the single, not x. It should be the answers. Yes, so it will like this. Then after that, we do the reshape, and we can get our desired single row. So this is here's idea why we do the reshape, and after the encoding, this is a matrix. After the encoding, and we will do reshape it again. After that, we will unwrap the data into the single column. You will see I will use this function and to get the single row data, which is here. So this step will be the data. And we have to do some after the coding, the total bits will be the different because we added the lots of the control symbols, control bits, and in order not mess, in order not mix the previously transmitted data, and after the encoding the data length, we will do some definition. We make some backup. So this will be the backup, the older. And we calculate the new. We use represented the new after encoding the length of the old word length. So this is after encoding the code word, and it's a single row called row vector. So we will update the number of the bits. So here, this is a basic idea. We do lots of transform, but the all steps are off in order to get the single row, and we will we can write now, and what will looks like. And definitely it has some mistake, but we only want to get this part, and you will see here. Here is binary dot. So again, I will show it like first one. Yes. After that, we do some reshape of the So it will be the n, and we have the 10 symbols. No. How do you say? Binary data is this binary data is the single column, and we will see here, and you will see here this is a single row. After that, we do some reshape with the binary data is it look like this, right? We will reshape it towards the 4 columns. After that, we do the multiplication. Use the Hamming function here, and we have the encoding matrix. We got the encoding here. After that, we do the reshape. Then we can get them to the single row. And so this is the basic idea and progress. What else is after the here we have to do some modified for the modulation, because we are not chance to do the modulation for the binary data. We have the new encoding the data, which is the encoding data. We just replace it. We just replace the find the SB data to replace the encoded data for the next part. And then we replace it and replace it. Replace it. No, this is the previous name. We don't substitute here. No, and here we have to replace it. So it's finished. And what else is we have the K here. However, previously we also had the K, so it's application. We have to use another letter to replace it. We use I. We find the K. Replace it. A with the I. I. No, this is yes. Was a K. So no more. And we can do some in our loop here. We have to do some modification with the received here. And what else I need to change it here? This is this part without Hamming coding, and we calculate the error value of the here. And we don't need this part. We remove this part with this is before the code calculate with so, and we will add some Hamming decoding. So after that, we will this we still need to save the without coding result, and we will compare it with the coding and compare the performance of which one is better. Add the separate NAND, which will be the enemy decoding. After that, we will use the move to the decoding format, and you will see we need for the decode, we need the code word names. We need the code word, and let's see for the non-systematic decode process, and we need the decoding matrix, and we check without errors, and we compare the syndrome, right? And so basic idea is we need the decoding matrix here, and this is for the non-systematic. But for the group code, we need to some index, and we need to find the logical index of the data symbol position. This is for the control symbol, and this is for the data symbol index, and the I will start from the 1 to the 7, and you will see here for here. But firstly, we compensate the decoding matrix, which is quite important here. And let's see. So what is the encoding matrix? Will be 0, 1, and 1, 0, 1, the 1, 0, 1, 0, and the last row. So and we will use the here use this function to find the module. So module 2 sum as the remainder divided by the 2, and this is code word, and the decoding matrix we use this one, and we will find out some errors in text here. After that, we will do the all of this one, and we open the group code here. So I will explain the details after we finish the main part with here timing decoding and what's the what the each step, what do we do, and so the code wordness we need to use the this function, and we need this one code wordness m and k, so 3 parameters are needed. However, firstly we still have to reshape the transmitted data, which is demodulated data with 0, and because it's still a single row vector, we have to reshape it as our desired matrix format. So the code word will be the, so we reshape the information over here, and we have this one. This one is the demodulated data after the receiver, and first one is here. After that, we do the row is m, which is similar to, no, this not same here. Here we use the k as our row, and here we use the m is 7, and for the column we use the total and divide by the m, and do the transpose, which is the matrix of the code words. To be decoded. And the decoded data will be the, and we use this one, decoded data. Here, after this operation, we will get the decoded data. So we just copy here, we just specify here, and here. Decoded data will use the decoded having this function, and the decoded and the code wordness matrix, and the m and the k. So this will be the decode data. After that, we need to do some reshape. Which is the decode and we need to wrap the data to the single row. single row. So, and we have to calculate the encoding after the decoding the errors, how many errors will happen, and we use the here. First I copy here, and for the I rename it. Here we use the decoded lab with the encoded with dot, and this case we use the decoded data with the so this with this data and compared with the binary data, and we calculate the number of the errors, and for the BER we also rename it as the one. This one, and it will compared with the previous M because we renamed it. M is the back of the order information bits, and we print it. So first one is the single to noise ratio, and the second is the uncoded BER. Uncoded, and next one is the coded BER. Coded BER, and with so first is the uncoded BER is the this one with the decoded. This one is a uncoded BER. After that, we have coded BER. So and so this is for the amplitude shift key case, and we have to add. For my case, I add all of them, which is more clear for you to one separate line, and just copy this part. First one is the here is the 2, and for the Codewords, and nothing will change here, and do reshape, and for the divided by M BER, and we add this part, which is so. No, firstly is the BASK, and the second is the BFSK. So for the byte with the BFSK, which is this one. And the encoding results here. So after that, once more we add again for the BPSK. So this will be the 3, and here we don't change anymore with the and the number of the errors is 3 divided by the M, and it will be the BPSK. After that, we will get 3. And here we have so this will be done for the loop here. After that, we can plot it, and we can plot them before the we have some reference to plot here. Just, and for the here, all plotter I will add in here, and the legend will be the first we add the legend with the value 1, 2, 3. So this will be the on channel without channel coding, and frequency without the channel channel without coding, and here. After that, we use copy different color with the first is Y, and the result will be the 1. The result will be 1, 1, 2, 2, 3, 3. And we will give them as the legend will be the coding. After coding, and firstly we command here And so it's done for the only one channel coding format, non-systematic group code. And if it's correct, it can be run. And after that, well, I would like to introduce the details for the decoding formats, what we do in the here. And first, let's see if it's run correct. Okay, there is a mistake here. Oh, the 990. So it will be the notice this is correct. Why is BFSK? Okay, here miss some. Correct. Yes. And you will see there on code and the code result. At the different synchronous ratio 3.5, and definitely code has some can improve the synchronous performance and lower bitrate error. Yes, it's correct. I see. For so yes, all of them will float successfully, and you will see for the red, blue, green. These three will for the uncoded ASK, FSK, PSK, and for the yellow and this one is pro and black. They are for the channel coding coding the result. So, and you will see here, well, for the BPSK after the coding, and it has a very big thing, gain between the encoding, and you will see even at around six single noise ratio, 6 decimal, and the BER will be the 0, and it's stop at here, which means its noise immunity very good, the good performance. And what else? For the amplitude shift can also get lots of the gain compared without the channel coding. Even it's better than the channel coded the frequency shift key here. However, if we zoom it and for the amplitude shifting, there is some problem, which is for here. You will see the channel code, the coded the amplitude shift key has the worst performance than the on 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 channel coded in the amplitude shift key case. which is always happen around the 1 signal to noise ratio, 1 dB. After that, it will be the After that, it will better. So I think, sorry, we have to notice that. So this case is only for the this case is only for the amplitude shift key, and other case we don't have such problem, right? And so it shows the ham encoding is it's really useful to increase the noise immunity performance. What I also would like to show what else is the decoding platform. What do we do? And you will see here, which is so how does find the logical index process, and we can do here. First, we will see the I will be the 1 to 7, and we use the logical function and find the it with the here, and you will see this is E1, right? Yes, this is E1. So we see E1, E2, C1, E3, C2, C4, C5. However, we will compare with the threshold, and we know the control symbol located at the power of the 2 position, and we get the index of this. Then the index of the control symbol will be the here 1 will be the index. If it's 0, so it's not our index. And we do some inverse here. Inverse to change the 0 to 1 and 1 to 0. So this for 1 will be our data index here, and we do some function here after that, and we use some to calculate the syndrome for each code word. We can see here the signal to noise value is the let's see this one. Okay, we can do it now, and by ourselves we just select one of them, and the code word names will be the 250,000. And we don't need this one. Such we hope want to get like 5 to 10. So firstly, we can see what is inside of the code word names. And yes, so we have the set for the each row will be the 7 bits, and the first column is the E1, and the second column is E2, the third column is C1. So this will be the start from the data symbol, and for the first false fourth column, there will also be the E3. After that, the C2, C3, C4. And what do we do in here after the use the matrix of multiplication, and we find out the syndrome, and we can see here what is this, if there will be no mistake, and the syndrome will be the 0, 0, 0, right? For the here, we know each syndrome represents the error, the position in the error vector, and we also know the 0, 0 syndrome will mean no errors happen. So let's see for the 10, 5 to 10, and 4 columns. And okay, it's not. Which after that, 5 to 10. And you will see each row their syndrome is 0, 0, 0. However, if I want to let it make some mistake, like to the specific, we manually specifically some mistake happened. First, we will specify the syndrome with the random like 0, 1, 1 at the C1. So I 0, 1, 1, and oh. So for here will be the always 0, 0, 0, and the third we no errors, just no errors, and the fourth I want to add one more error here. I change the position with a 1, 1, 0, 1, 1, 0. How many do we have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, and 5. And the last one is will be 6. Right? We add some errors at the first row and fourth row, and we know the position is at the 0, 1 at the C1, and for the 1, 1, 0 is the C3. So we will use some check. We will use some the how is here is the Codewords with and we here we use this function to check it, what will looks like. And in my case, we are is the 1 A, and it will be the I just randomly specifically is as B, and in my case, R is the 3 minus 1, which will be the 2, 2, and 1, and 0. So, and it's same with the last practical exercise. We need to find out its how to say the power of the position. Let's see, and you will see here. We find out the position is this. This is the third position and the sixth position. Let's check it. Yes, the third position and the sixth position. Use this formula. What else? We will find out the index, match the position for the error index. We will find out the error index. So uh, so this will be the B, and B. And we can specify. Yes, this will double check it. Actually, from this step, we already know the position of the index, and this step also, how do you say, another step is the we know to make sure the to give the index the new parameters here, parameters here. After that, we need the arrow vector. Uh, we will manually do specific here. However, for the arrow vector, and we add one is the 000 with the zero syndrome, which means uh, according to here, which the arrow vector is the no errors happened. So arrow vector also is 0. After that, we have the identity matrix, right? According to the syndrome. So this is the arrow vector, and we will use some uh, Codewords plus the, so just remember in this case the Codewords will be the 5 to 10, and we will add some arrow vector index. In my index is C. C. Why do we plus 1? Because in my lab it starts from 1 or 0. So here we still need to add 1. And our calculated the index, it starts from the 0. And let's see. So we add them together. And you will see some here, 2 and 2. We know the error, where is the error's position in here. The third position and the sixth position. Now we use the remainder function to calculate to correct the result. To correct this mistake, I only replace in the here. Right? So you will see 2 is changed to the 0, and use the reminder function, we change the to the 0. So that's good. And if you don't believe it, we can just compare with the previously case Codewords, right? It will be the same with the Codewords with oh no, it still be the no mistake here. Oh, 1 to the 0 to 1. However, we have to do, I changed the 1 0 1 0 1 0 1 0. And what else here? And for the year, this step will be the Codewords length here. Yes, it looks like some C++, but in my case, I do correct to correct the one errors happened here, and we will use the code word here, code word length words, and what else do I miss here? For the 0, here is different, and here. So it seems like it correct as the 1, 0, not 1. But for the previous case, what I don't remember for the 1, 0. Is 0. 1, 1, 0, 1. So I plus 1 to the index with 2, which is with mistake here. Error vector. Five to 10. We have the this is identity matrix with the here mistake with here. So sorry, I cannot find out where is a mistake. If you will ask Dr. Nanus, and he will explain more if you have.
Sorry, I'm here. What's
yes,
this program?
Dr. Yes, Dr. Nanus. Here I used randomly to calculate the mistake, and you will find the after the 2 and it's 0. However, in the previous case, it's 1. How it's correct after remainder? It's incorrect.
Wait a minute. So code word without error vector has 1, and with error vector it has 0. Well, looks
After
like just
yeah.
so that is, or wasn't it? Wait a minute. So C plus 1. What and what was C variable? Ah, that
yes.
was symbol.
Yeah. And it's correct. It do the correct the errors. However, after the remainder calculation, it the remainder is the 2. Remainder is 0. However,
Yes.
previous case the remainder is 1. Oh, it's
no. Wait a minute. What you are looking at here is now code word without error vector, and above is code word and error. So basically, cdvrd is a real code word, and what is this reminder cdvrd plus error vector is the same code words with introduced errors, which is correct. Yes, the error indeed converts this one into 0. So that's how this error is happening in those positions.
Yes.
So it's correct. No mistake there.
Oh. So
because error vector inverts specific symbols. Yes, and it turns out exactly these symbols, those were inverted during this operation of adding error vector. So that happened because you added error vector.
Okay. So it's inverse. So I understand. Thank you.
It's okay.
Yeah. And this is the basic idea of the decoding process of the for the group code, and for the group systematic encoding and decoding, and for the non-systematic. Oh no, sorry. This is for the non-systematic code case, and for the systematic code coordinates, we have to rearrange the encoding matrix position, right? And for the here we put the first 4 columns as our data, and the last 3 as our control. So let's do it. And so the first 4 is identity matrix. That will be the easy to see. And for the 1, zero. And for the this is 1, 1, 0. And for the 1, 0, 1. And for the 1, and we keep save it. And usually we have to rearrange the decoding matrix. However, in this case, we add some position change here. We open the command here, and I will introduce how it works. And it's use the backup of the Codewords. And let's see, we still choose the donor for the 5, and with which is this. This is the code one as I randomly choose the 5 of them as our this backup, and we will use some index for here, which is here, which is and -1 and r, and you will see this is the last 3 columns. And in previous case, this DMP is still the non-systematic code. So the last code will be the data vectors, right? And we will use this as our index of the data. So it will looks like here with our case 15 to 20 and the index with so what is our index is yeah, okay, index is same, so it will be this one, and the Codewords analysis is the first three column, and for here, this is the control index of this bond. 15 to 20, and you will see here, this is 0 here, here, and the last signature. So actually, it changes the position of your Codewords. I already write down this one, and in order we don't need to change the decoding matrix again. We rearrange the position of the our Codewords, like we use here this this is for the non-systematic arrangement position, and you will see here is E1, E2, C1, E3, C2, C3, C4. That's some position, change the position. In my case, we have 7 Codewords and R and will be the 7. 7 minus 3 is 4. 4 plus 1 is 5. 5 to 7, which means 5, 6, 7, which is the last 5 to 7, which is the last 3 case, will be the last 3. And it will equal to the index of the data, and you will see here the index. Oh no, sorry, index of the control symbol. So it will be the E1, E2, E3, and I change it as C2, C3, C4. After that, we have the one index with 1, 2, 4, and you will see here the 1, 2, 4, and this is data, and for the data is the 1, 2, 4, which is the data is C1, C2, C3, C4, and we will use the place with the index of the index of the control symbols here. Yes. So it will be U1, E3, E2, E3. So this is the that we will give this new position case. And if we use this new position case, we don't have to rearrange the decoding matrix again. So it will be the same. And we keep it the decoding matrix. We don't change it, and we can write again. Keep it correct. And for the we don't do we already rearrange the position, and let's write again. And yes, it seems a little bit So
Hello? You are quiet and the screen is not showing. Looks like
no,
some
I
problems.
still not finished.
Ah,
Yeah,
it just ended so suddenly.
Well, I'm Ronnie. Yes, both you will see. For I think it's a little bit different with non-systematic coding formats, and this is for the systematic coding result. And well, it's hard to say which one is better, and you will need to compare with the difference with them. However, it's true that the coding absolutely increase the gain, right? And you will see here here previously, I think it's here at 6.5 after the coding and for the BPSK. And
sorry, your
so
screen is not
still really
frozen.
good,
It's frozen
and,
on some previous slide, and it's not updating anymore. And also, you are lagging in the voice, so looks
what?
like
Sorry?
some problem with internet again happening in your place. Maybe you can try to reconnect.
You cannot see my
this
screen?
group. Well, it's still the same as it was a few minutes ago.
What about now?
Maybe you need to start again sharing screen. It looks like it's frozen.
Okay. Can you see my screen?
It's not yet.
Hello?
No screen yet.
No screen?
No screen, no. Well, don't worry. Sometimes this happens. It didn't happen too long. Okay, so I understand you have got
But I
group
will
code.
I will finish the yes, but I finished the record, then you you will find the record on internet if you don't miss some part. Okay.
So I think yes, we can finish this record now.